Hey everyone. We'll get started in a few minutes. So for now, just try and see if you can do the warm-up problem. So I'm just gonna just go over like the first couple of steps. So how you might interpret this question. So it gives us two functions. The first one is the altitude or the height of rocket one. And then the second is for the second rocket. So then it asks to obtain a function for the difference in altitude between the two rockets. So all we have to do is subtract the two functions, the two heights of the rockets, and then that'll get us the difference. So we could do something like a1 of t minus a2 of t, and then that will equal the difference. We'll just say this difference. I'll just use d for distance, d of t. So if you were to set it up, so you'd have negative 5t squared plus 100t plus 1000. That's a1. And we subtract negative 5t squared plus 75t plus 1200. So that's going to be our distance, our difference. So, and we just have to do the subtraction. Okay, so we have negative 5t squared minus negative 5t squared. So that's equal to plus 5t squared. So that just cancels out. Then we have 100, 75. Just fix that. We have 100t minus 75t. So we get 25t. And then we have 1000 minus 1200. So that's minus 200. So this is going to be our function for the difference between the two rockets when we have time as our independent variable. So for example, at, let's say, time equals 0, so we'll say d of 0, that's going to be equal to negative 200. So there's going to be a difference, going to be a difference of 200 meters, I guess, when at the beginning. So before they even, I guess that doesn't really make sense, but yeah, that's what it would say at the beginning. And then you could calculate at d is equal to 8 seconds. You get a difference of 0. So after 8 seconds, the two rockets would be at the same height. So yeah, so today we're just going to be going over different operations with what we call rational expressions. So this right over here, that would be considered a rational expression. Um, in other words, we'll basically just be doing addition, subtraction, multiplication, and division of polynomials. Okay, so here's another quick example. We have addition and subtraction here. So same thing. You want to just combine the like terms. So we have the x squares go with the x squares. So let's just start with that. So 2x squared minus x squared plus x squared, that's just going to be 2x squared. And then we have negative 4x minus negative 3x. So that's plus 3x. That's negative x. And then there's no x term here, so we don't do anything there. And then lastly, the constants, we have 3 minus 2 is 1. Then 1 minus 1 is just 0. So that should be it. And then we can finally just factor the x if we really wanted to. So you get 2x minus 1. That's not really necessary. So that's pretty easy. Just basically all you have to do for this is just practice it, just get good at it. So here's another one. Determine whether each pair of functions is equivalent. Because this is a little bit different. You could simplify both f of x and g of x, right? So you can subtract these and combine, and you can add these and then see if the result is the same. The results are the same. So that's the first way. We could do it the first way. Okay, we have f of x is equal to 2x squared. And then we have plus 4x, right? 7 minus 3x. And then we have minus 9, negative 2 minus 7. Oops. Okay, and then g of x, same thing. We have x squared plus x squared is pencil's not responding. Okay, we have 2x squared plus 4x and then minus 5. And if you compare, you can see that the constants are not lining up. So this pair of function is this pair of functions is not equivalent. So that's the first way. The second way would be to substitute a value of x and see if the result, the value is equal. So for example, if I sub in x is equal to 0, 0 is a nice number because it's going to just cancel out all the terms with x. And then if I also do the same for g of x when x equals 0, so we can see that this is going to get canceled out. This is going to get canceled out. This is also going to get canceled out. So we just have to do negative 2 minus 7 is just negative 9. G of x, we can do the same. Cross out all of the x terms. And then you just have to do 12 minus 17, which is negative 5. And we can see that for the same value of x, they have a different y value. Graphically, if we have x equals 0, and then f of 0 was negative 5 or negative 9, and then g of 0 is negative 5, it's going to look something like this. And so you can clearly see they can't be on the same, they're probably not going to be on the same function. Yeah. So that's also, I guess, a faster way of doing it potentially. But I would say in general, the first way is going to be more applicable. I think the second way is it's it might not work all the time, I guess. So yeah. Okay, and then this is a very interesting like thinking problem. So for each pair of functions, label the pairs as equivalent, non-equivalent, or cannot be determined. So for the first one here, they tell us that f of 2 is equal to g of 2. Um, so that you might think that this means that they're equivalent, especially since we just did an example using this, right, where f of 0 is equal to g of, we had to show that whether or not f of 0 was equal to g of 0. And because it wasn't, we knew it wasn't equivalent. But we actually can't assume that in this case. Because if you just think of it graphically, so when f of 2 is equal to, let's say it's equal to 1. Oh, wait, so then that would look something like this. And then g of 2, let's say, is also the same point, right? Because they're equal. So we're saying, f of 2 equals 1, g of 2 also equals 1. You can think of this point as a point of intersection, right? That was kind of something you've learned in grade 9 and also 10. So that's kind of nice. But you can't assume that they're the same function because you could have two different functions, right? Two different functions can have a point of intersection. It's possible that you have the same function, right? But it's not guaranteed, right? I could also do this with a quadratic. It might look something like that, right? There is a point of intersection here, but it doesn't mean that they're the same function. So first one, we'll just say, we'll say cannot be determined. CBD. Okay, for part B, we have h of 3 is equal to g of 4. So h of 3 equals g of 4. It's kind of similar to part A. They don't give us enough information to know for sure. So again, if you look at the graphical approach, let's say h of 3 equals 1, and then g of 4 is equal to also 1, because they tell us they're equal. Again, you could have two different functions. Like you could have a linear function, right? A system of equations that looks something like this, right? But you could actually also have maybe a parabola, and you have two of the same parabolas, and so both functions would be equal. But the idea is that the point here is that you don't know for sure which is which. You can't say for sure that they're equivalent or non-equivalent. So again, cannot be determined. For C, things are a little bit better. So they tell you that J of 8 does not equal K of 8. So again, if we look at our example, let's say this is at x equals 8. Let's say J of 8 is at 1, and then K of 8 is at 2, so they're not equal. So I guess in this example, because they're not equal, by definition, it's impossible for these functions to ever be the same, right? There's no way to draw a function where both of these points are on the same line. Now you might think that if I drew like a straight line across both of these points, then the two functions could potentially be equivalent. But the problem is this is not a function, right? Because the vertical line test, for the same value of x, you have two different values of y. So it's not a function anymore. And if you drew upside down, or not an upside down, but a sideways parabola, again, this doesn't work because it's not a function. And so yeah, no two functions could ever be equivalent in this case. And so we can confidently say that it's going to be non-equivalent. Okay, and then for D, L of 5 does not equal M of 7. So the problem here is that the X values that they give us are not the same. So we're not going to have enough information to know for sure. Again, let's say that this is at X equals 5 and this is equal to X equals 7. They tell us they're not equal, so we might see something like this. So the problem is, yeah, you could argue that you could draw two functions that are not the same, like what I've done here. But you could also draw a straight line that goes through both of these points. And then my second line would also be the same line. So I'd have two equivalent functions. And that would also work, right? Because in this sort of, on this line, it contains different values for L of 5 equals something, and then M of 7 equals something. So that's like a counterexample. So again, cannot be determined, CBD. Okay, and then the last part. So this is going to be referring back to domain. So the domain, again, is just the set that contains all the X values of a function. And they tell us that the two functions are equal for all values of X in their domain. So this is directly telling us that N of X will always equal P of X for every single value of X. So basically, they're telling us that the two functions are the same. Because I can't, if I had, let's say, a parabola as my first function, I can't draw a function that's different to it because all of the values, right, all the y values have to be equal to each other for every value of x. So every single value of x. So I'm forced to draw an equivalent function, basically. So this one I can say is equivalent. Okay. So that's kind of it can be kind of confusing, but trying to, graph it and just think of some examples is really helpful. Okay, moving on to multiplying and dividing. So determine a simplified function that represents the volume of the given box. So volume is equal to x plus 3 times x plus 1 times x plus 2. And then basically we just have to use, what was it called again? Cast, or no, not cast. That's for trigonometry. There was like a rule for it. I kind of don't remember the name. But you multiply this with this with that in this pattern. Yeah, FOIL. Yeah. You can use FOIL and you just multiply. So we have x squared plus 3x plus x plus 3. And then times x plus 2. I'm just going to combine this to 4x. Okay, and then this becomes x cubed plus 4x squared plus 3x plus 2x squared plus 8x plus 6. So kind of tedious, but just combine the like terms. You get 6x squared. Yeah, something like that. And that is our volume function. Okay, and then here's another equivalency question. So is this over here equal to that? And if you look at it closely, you'll notice that if you look at the coefficients, when you square these coefficients, you get values that are equal to the coefficients of the other expression, right? 2 squared equals 4, 3 squared equals 9, 4 squared equals 16. So that might feel like they might be equivalent, but if you just think about how you would multiply it, right? When you square this, that's just equal to an expression that looks like this. And you'll find that there's a lot more terms than just these three. So you will get these three terms and you'll have a bunch of extra terms. Like I'll just do a little bit. I won't do the full thing. So you'll have 4x squared plus, 6xy, which is already something that this doesn't contain, plus 8xz, and so on. You're going to have a lot of combinations, and they're never going to cancel out because you don't have a subtraction sign. So these are going to be in your result, basically. So no, these are not equivalent. Okay. A rectangle is twice as long as it is wide. Predict how the area will change if the length of the rectangle is increased by 1 and the width is decreased by 1. Write an expression for the change in area and interpret the result. So a word problem, you just have to think about what it's telling you. Let me just draw this a little bit better. We have the, let's say this is the width, this is the length. The area of this rectangle is equal to the width times its length. But they tell us that these lengths change. So the length is increased by 1. So we have L plus 1. And I'll draw it here too. So L plus 1. And then the width is also increased or decreased by 1. So it's going to look something like this. So we have the length plus 1 times the width minus 1. That's the new area. And then we just have to write an expression. So we have length times width. And I'll just write it in the other order. Width times length plus width minus length minus 1. And yeah, that's pretty much it. So the area, so they also ask us to interpret the result. So the area, you can't really say whether or not, can you just replace length by 2w? Let me see here. Length by 2w. So wait, like how do you know length is equal to 2 times the width? Um, I don't think you'd be able to say that unless I'm not seeing something here. Oh, wait, it does? Oh yeah, it does say this. Okay. It does tell you. Okay, so it also tells you that a rectangle is twice as long as it is wide. Okay. Yeah, okay. Sorry, yeah, I did miss that. Let's see here. So we have length is equal to 2w. Yeah. Okay, so we can substitute this piece of information. Let's see here. So we'll have width times 2w plus w minus 2w minus 1. Okay, yeah. So we get 2w squared plus minus w minus 1 as the new area. And I'll also do the same for the original area. So this is just equal to 2w squared. Okay. Interesting. So it's gonna be reduced by the width and then minus 1. Okay, so now we can actually interpret the result. Because I was gonna say that you don't have enough information. But actually, when you know that the length originally was 2 times the width, you can actually say that when you make these changes, the area is actually going to go down. So that would make a lot more sense because they asked to interpret the result. Okay. So yeah, the main thing of that was just to multiply and then substitute. So yeah, these problems are pretty straightforward. Okay, and then we have one more here. So the kinetic energy of an object is given by E equals 1/2 mv squared, where m represents the mass and v represents its speed. So write a simplified expression for the kinetic energy of the object if its mass is increased by x. So we have energy equals 1/2 m plus x. So that's increased by x, and then v squared. I want simplified expression. I guess just for practice, we'll multiply this. So 1/2 m plus, to be honest, this is already pretty simplified. I think I'm going to keep it because if I multiplied it, it would just be no longer simplified. Okay, so for part B, its speed is increased by y. So we just do the same thing. 1/2 m v plus y squared. We make sure that the y is also being squared. Okay. That's actually pretty much it. Okay, we're getting through this a lot faster than I anticipated. So, okay, the next part is factoring. So again, this is all kind of just review, probably from grade 10. So for something like this, we have a trinomial, right? Because it has 3 terms with the x squared coefficient being 1. So we know that the factored form is going to look something like this, where s and r are just, constants. And s times r needs to equal the constant here. And then s plus r needs to equal the -1 coefficient. So yeah. So you can just think of some numbers. You could say maybe -6 plus 5 would probably work. So -6 plus 5 equals -1. -6 times 5 equals -30. So S and R is equal to -6 and 5. So then you would say this is equal to x minus 6 times x plus 5. This example here, you might notice that 2 of these coefficients are perfect squares, the 9 and the 25. So you might recognize this pattern as a perfect square trinomial. So you can kind of just do this in your head. You could just think 3x plus 5 is probably squared, is probably going to be the answer. But if you don't recognize the form, that's fine. You can just do it. You can try doing it. Okay, that would actually be more complicated. Yeah, there's another way to do it. I'll do that in another example. Okay, then we have over here B. So this one's pretty simple. You can factor out, I guess you could just factor out a 2. So 2 times 9x minus 25. Okay. And then we can actually factor this further. We can, because we see here that we have a difference of squares, right? The 9x squared is basically just 3x squared. And then, of course, the 25 is just 5 squared. So we can actually say that this is a difference of squares. So we could say that this is equal to 3x plus 5 times 3x minus 5, right? A plus b times a minus b, right? So that's going to allow us to simplify, factor this further. Okay, I'm kind of doing this out of order, but okay, E. Okay, this is the example where the x squared coefficient does not equal 1. So it's a little bit more complicated. There's a few ways, I guess there's two main ways to do it. So, okay, the first way is this. So you know that the form is going to be, of the answer is going to be, in this case, you know it's going to be 2x. And then here there's going to be an x, right? Because x times 2x is 2x squared. Then you know that you know that you're going to have constants. We'll just say r and s again. And the idea is kind of the same thing. R times s should equal 3. But then r plus s is going to be slightly different. I'm pretty sure. You can try finding r plus s. R plus s is going to be kind of weird. Let me think here. So I guess you would have like 2 times s plus r. Yeah, you'd have to say 2 times s plus r equals 1, this coefficient. So that's kind of weird. I don't really like doing it this way. So in my opinion, there's just a better way of doing it, which is to do something called a crisscross method. So again, you you basically just use the same sort of idea that like you have an 2x and then an x. And then the idea is basically you just try different values. So the setup is just easier basically. So you can just try different values over here such that these two values equals 3 basically. So it's basically the same thing, but I think that it's just a little bit cleaner to do it this way. So you could just try 1 and 3. And so let's see here. We have 1. Oh, no, that's not going to work. You have 1 and 3. Oh, that's also not going to work. So it's possible this is not factorable, actually. Yeah, because you can't make this a negative. Okay, actually, I just realized this is not factorable. So, okay. So we'll just say not factorable. So yeah, that's also something they might give you. They might give you something that you just can't factor. So you have to recognize when something is not factorable, basically. Oh, that's probably why it's the last question as well. Okay. And then for part C, we have 10x squared minus x minus 3. Okay. This one should be factorable. So I'm going to try 2x and 5x, since I know 2 times 5 is 10, and then we can just try values that multiply to -3. So I'm going to try maybe -3 here and then a 1 here. That seems to work because we have, so what I'm doing then is I'm going to multiply these together. So I get 2x times -3 is equal to -6x. And then 1 times 5x is equal to positive 5x. And then when I add these two values together, I get -x, which equals this middle part. So I'm basically just doing trial and error, just doing some guesses until it works. So this works. And then lastly, I just take these two and I put them in the bracket. So 2x plus 1 times 5x minus 3. So it's just a really neat way to sort of do trial and error. So the crisscross method is mostly just good because of its setup. So it's a very clean way of doing trial and error. And you can do it really quickly once you get good at it. Okay. Okay, we have another factoring one. So for this one, your first instinct might be to factor all of these, right? Factor out the x. So you might get like, x squared plus x plus 1 plus 1. And I guess that's fine, but you could actually factor this a lot better by instead, and actually I'll keep that so you can see the difference. This is one way you could do it, but there's a better way to factor it, which is to group them into two groups like this. So again, we're going to factor out the x squared, and we're going to get x plus 1. So we get x squared times x plus 1 plus x plus 1. We can't really factor anything here. But we do see that we have matching x plus 1 factors in the two terms, which means we can factor it out. So we can factor out the x plus 1 and get x squared plus 1, because you could think of the coefficient here as just not a coefficient, but you could think of it as being multiplied by 1. So that is just, I think, a lot better. It's a lot more factored compared to this. So grouping can be helpful. So here's another example of grouping. This time, you want to notice that this is going to be, I think, a perfect square trinomial. Yeah, this is going to be factorable. And then this is going to be a perfect square. 4y squared, that's just 2y and then everything squared. So you might already notice that you're probably going to need to use difference of squares. And so if we factor the first part, the trinomial, we get x minus 3 squared, right? So it is a perfect square trinomial. The second part is 4y squared, which I already said is equal to 2y and then squared everything. So now we have a difference of squares. So we can just say x minus 3 plus 2y times x minus 3 minus 2y. Yeah. So that's going to be factored. So yeah, try and look for these patterns like perfect squares, trinomials. Because the goal is to basically factor it as much as possible. So again, in this example here, this is much better, I would say, than this, because you have a plus 1 here, so it's not fully factored, but this is fully factored. And so that's going to be helpful if you're trying to figure out, we'll see later, when you're trying to figure out restrictions of functions, or when you're just trying to simplify. Like if this was in a fraction and you had more stuff at the bottom, you could potentially cancel out stuff. So that's why we want to factor as much as possible. Okay, and then we have simplifying rational functions. Okay, I think before I start this, we're going to just take a quick break. So yeah, this one, we're going to kind of go back to graphing a little bit. but we'll take a quick 5-minute break. All right, so let's get back to it. All right, so this one we're gonna do a little bit of graphing. All right, so it asks us to write the simplified expression for this fraction, right? And what we're going to want to do is, first of all, factor the numerator and denominator. So we have P of n is equal to, at the top, we can factor out the 3 and also an n squared. So we'll get n minus 1. In the denominator, we can factor out a 4. So just take a look at the constants first, and then look at the variable. We can factor out an n. So we have what's remaining would be 2n squared minus 3n plus 1. All right. And it doesn't look like we can cancel anything out just yet, but this looks like it could be factorable. So I'm going to keep going. So 3n squared, n minus 1, 4n times, and here we can use the crisscross method. We probably have a 2n and a n. Okay, and then it says plus 1, so it's either going to be 1 times 1 or -1 times -1. And because this coefficient is -3, it's probably going to be -1 times -1. And yeah, that is the case. So we have 2n minus 1 times n minus 1 as the factored form. And now we do see that we can cancel out the n minus 1. And again, we can cancel this out because we have everything fully factorized, right? We don't have something that like a plus 1 here, because if we had a plus 1, we wouldn't be able to do this anymore. Everything has to be factored. Okay, and then we can also cancel out the n's, kind of, like so. So we get 3n over 4 times 2n minus 1. And that is the fully factored form of this function. I'm just going to move it to the side a little bit. Okay, and then I also wrote here, don't forget restrictions and state the domain. So the restrictions to a function are basically I guess the values that don't exist. So like when we say, for example, there's like an asymptote, right? If you remember for the reciprocal functions, like something like this, there's a vertical asymptote, right? Where there is just no x value of 0, right? X cannot equal to 0, right? And remember that in our domain, right, when we said, x is real, and we also said that x cannot be equal to 0. So that's basically what a restriction is. An asymptote is one of them. So the question now is, how do we know the restrictions from the function here? So if you remember, right, in the reciprocal function, x cannot equal 0 because when that happens, you get 1 divided by 0, which is undefined. You can't divide something by 0. And the reason is just because it can be equal to two values. It could be equal to infinity or negative infinity. So because it doesn't have a single value, and also that infinity is not really a number, so there's just undefined. So we have to figure out values of n that causes the denominator to be equal to 0. Now, if you look over here, we can see that when 2n minus 1 equals 0, the value is going to be undefined. We get 0 in the denominator. So we can solve for n, and we get n is equal to 1/2. Oops. So that means that when n is equal to 1/2, we get an undefined value. So that's our first restriction. N cannot equal 1/2. But there's actually more restrictions than just 1/2, because you also have to consider the previous sort of unsimplified form of the function. So you have to also look at it over here. So you see that we've already considered this, 2n minus 1 equals 0. So we don't need to consider that anymore. But we haven't looked at n equals or n minus 1. So when n minus 1 equals 0, we also have an undefined value. So that's when n is equal to 1. So that means we can add 1 to our list of values of n that it cannot be. So n also can't equal positive 1. And then also over here, for n, we see that when n is equal to 0, it also makes the denominator equal to 0. So again, we haven't considered it because we've simplified it over here. So we have to consider this as well. So when n is equal to 0, that's also going to be a restriction. So n also cannot be equal to 0. And that seems to be it, because here you can't really get anything. And here you can't really get anything new either. So these are our 3 values for our restrictions. And then the domain is going to be x is real such that, and also that n cannot be equal to 0, 1/2, or 1. So those are its restrictions. But the thing is that these restrictions are not going to be the same, right? So far we've learned about one kind of restriction, which is the asymptote, basically, where there's where you kind of just have like an entire sort of line that just never gets reached. But you actually don't have that for all of these. So, okay, this is kind of messy, but if we were to, I guess you could graph this. I don't really have space here. Okay, I'm just gonna show you my other screen where I've graphed this function, and then you can kind of see what I mean by that these restrictions are not the same. So let me just share my other screen. All right. So here's the graph. It's the black lines. So yeah, this looks like a reciprocal function. And you do see a vertical asymptote at x is equal to 1/2. So that was one of the values we calculated. But you also see restrictions, I guess, at x equals 0 and x equals 1, which again, we've calculated algebraically. But you can see that the restrictions look different, right? At x equals 1/2, we have a vertical asymptote. But then you don't have the same thing at 1 and 0. Instead, you have what's known as a hole. So this sort of circle, this empty, unfilled circle, just means that there is no value at this point. So this is at 1 comma undefined. There is no point here on the graph. And this point here is also known on the graph. So these are called holes. And so they are kind of different. So let's just remember that. So 0 and 1 are holes. So why is that? Let's just take a look back at the whiteboard. So 0 and 1 are holes. Okay. So if we take a look at the values here, right? So 0 and 1 are wholes. You can see that the values of 0 and 1 were obtained from, this sort of unsimplified form, right? 0 was also taken from the 4n here, right? But then when you finally simplify it, all of these restrictions actually go away, right? So in the final simplified form, you only get n equals 1/2 as a restriction. And so the idea is basically that if you simplified all of these and then these restrictions sort of went away, then you get a whole. But if even in your most simplified sort of form, the restriction is still there, so that would be when n equals 1/2, then you get an asymptote. And so that's kind of the idea that you can sort of tell whether or not it's a whole or if it's an asymptote. So here's another example. So simplify, state in your restrictions. So we can simplify, we can cancel out the constants first. So we have 5. I guess we'll just say, yeah, 5, -5. Then x to the 4, x to the 7, we have x to the 3 on the bottom. And then y to the 3 over y, that's going to be y to the 2 at the top. So that's going to be the simplified form. Now, restrictions, we can see from here, we can see that x cannot be equal to, my pencil's not responding again. X cannot be equal to 0. But then if we consider the unsimplified form, we see that y also cannot be equal to 0. So those are its restrictions. And that's pretty much it. We're not going to graph this because it has y over here. So yeah, you can't really, I guess you could solve for y, but they don't really intend us to do that. So let me keep going. Okay, then we have adding and subtracting rational functions. This is probably the most annoying operation to do. So we're going to try, so when they say simplify this expression, they want us to combine all of this into a single fraction. So to do that, we're going to have to find the lowest common denominator, the LCD. And we see out of these three, it looks like it's going to be 24. So again, look at the constants first, 8, 4, 6. It's going to be 24 x cubed. So that's our, this is our lowest common denominator. So now we multiply everything by this. So 24x cubed, we had to multiply it by 3 and x. So 3x times 3. So that's just going to be 9x plus, now here we had to multiply 4x by 6x squared. And then over here, we had to multiply 5 by 4. That's it, actually, right? So 4 times 6x cubed is equal to 24x cubed. Okay, and then 4 times 5 is 20. Okay, then we combine, we get 6x squared plus 9x minus 20 over 24x cubed. I feel like we can also factor this. So crisscross method, that might not actually work, but we'll try it anyway. So 2x and 3x, 20 is 10 and 2. That doesn't work. It's too large. You try 5 and 4. It's also too large. 5 and 4. Nope, too large. Yeah, 15 minus 8. It's not, it's close. And then most likely x times 6x is not going to work either. We have 10 and 2. That's, yeah, not going to work. Okay, and then 4 and 5, definitely not going to work. Okay, doesn't seem to be factorable, so I'm just going to leave it. Yeah, so I guess that's that's it. Now for restrictions, let me just see something here. Okay, so for restrictions, we really just have one, which is x cannot be equal to 0. When you look at all the unsimplified forms, it's all the same. So it's just going to be x does not equal 0. And this is going to be an asymptote because even in the simplified form, this restriction is still exists. So it's going to be an asymptote. It's going to look something probably like this, where there's an asymptote in the middle. And I've also graphed it, and that's basically what it looks like. So yeah, I'm just not going to show that. Wait, let me just, there we go. Okay. Let me just see how many more. Okay. So here's another one. Simplify. So this is a little bit more involved. We're gonna have to find the lowest common denominator of these two. And the idea is it's a little bit hard to tell. You're just looking at it like this. And so it's gonna be easier if we factor these. So I'm gonna factor t squared minus 1. I'll write it over here. So t squared minus 1, that's gonna be the difference of squares. T plus 1, t minus 1. This trinomial here I can simplify to t plus 4 times t minus 1. So we can see that we want these two denominators to be equal, right? So we're going to have to multiply them by something. We see that they both have a t minus 1, but then this one over here lacks a t plus 4, and then this over here lacks a t plus 1. So I'm going to give them that. And now they're going to be the same after I multiply them by the blue part that I added. So we're going to do that now. So we have 2t times t plus 4 minus t plus 2 times t plus 1 over the new, the common denominator, which is just t plus 4 times t plus 1 times t minus 1. And while it would be nice to sort of cancel out anything, it doesn't look like you can cancel out anything here. Can't really simplify, unfortunately. So I think that's all. I'm going to leave it at that. Yeah. So restrictions. We have t cannot equal 1, -1, -4. Right? So you just look at these, and that's it pretty much. And then the unsimplified form, you can't get anything new from there. So these are the three asymptotes. And they're all going to be vertical asymptotes because they persist in the simplified form. And just to make sure that's correct, we can also look at the graphed version. I'll just quickly share my screen. Quickly share the graph. Oh, not this one. So we can see here that, so this is the unsimplified form. And we can see we have three vertical asymptotes here at -4, -1, and +1. So that does fit, that does match what we calculated. All right. Just share the whiteboard again. All right. So I think the last thing we have today is just operations with radicals. So technically, radicals are not rational expressions since they're irrational, usually. But it's just helpful to also just know how to do this. It's going to help for next week's class, where we're going to look at the inverse of a quadratic. So here it asks us to express each of the following as a mixed radical in lowest terms, right? And that kind of sounds like a mixed fraction, right? Mixed fraction. And it's similar. So a mixed fraction is where you take something like 3 over 2 and you express it as 1 and 1/2. So that's a mixed fraction because you have, I guess, a non-fraction and then also a fraction. So you're mixing the two together. With the radical, it's the same thing. With like the square root and stuff, it's the same thing. So part A, we have the square root of 72. So we can say that this is equal to the square root of 9 times 8. And a rule that you can do is if you have something like this, you can write it, you can sort of separate it as the square root of 9 times the square root of 8. And then you can just simplify. So the square root of 9 is 3. And then the square root of 8, well, you can actually do the same thing. 8 is equal to 4 times 2, which is just the square root of 4 times the square root of 2. And so you get 3 times the square root of 4 is 2. So 3 times 2 is 6 times the square root of 2. So there's your mixed radical. You have a non-radical mixed with a radical. So again, we can do the same thing here. We have 5 times 3 times 9, the square root of 3 times 9, which is just 5 times the square root of 9 times the square root of 3. That's equal to 15 root 3. So that's the lowest terms. So in that case, we can also reverse it. So if they have this, we can say that this is equal to the square root of 5 times 11, which is equal to the square root of 55. Here we can, what we can do here is, like the mixed fractions, we want to focus on the same types of values here. So we have the constants. So -4 times +2 is -8. Then we focus on the radicals. So root 6 times root 6, that's the square root of 6 times 6, which is equal to -8 times 6, which is equal to -48. So yeah, we can kind of just do that separately. Okay, this is so here we have them asking us to calculate the perimeter. So perimeter is going to equal the square root of 8 plus the square root of 18 plus root 12 plus 2 root 3. And that's it. So you can't add them like so, right? You can't do that right now. You have to, first of all, simplify this. So the first one here, I'm going to simplify to 2 root 2, right? Because 8 is equal to 2 times 4. The square root of 4 is 2. So 2 root 2 plus, now root 18 is equal to root 2 times 9. So I can take out the 9 and get a 3. So 3 root 2 plus, here we have 3 times 4 equals 12, so we can get rid of that. Oh, wait. And then we have 2 root 3. can't really simplify that. We can now factor out the root 2 here. So we get root 2 times 2 plus 3. That's just equal to 5 root 2. Actually, yeah, I didn't have to do all that. Just 5 root 2. Right, you just add them basically. Right, like 2x plus 3x basically. 5x. 5 root 2 plus 4 root 3. And yeah, that's as simplified as you're going to get it. Okay. All right, and then you can also do FOIL with radicals. This is going to actually come up a little bit more often later on. So again, FOIL, we do 3 times 2 is equal to 6. Then plus 3 times root 24. Minus 2 times root 6 minus root 6 times 24, right? We can just do that right now. All right, and then we have to simplify all of this. So this 24, let's see if we can simplify this. This is equal to 4 times 6. So we can get rid of that 6, or we can get rid of that 4. We get 2 root 6. And root 6 is not simplifiable. Minus 2 root 6 minus. Okay, the 24 we can get rid of a 4. So 2 root 6 times 6. So we get just 2 times 6. All right, so we get 6 plus 2. I guess I'll just do it like this. Yeah, I've kind of made it confusing for myself, but you get, okay, I'll just multiply this. So you get 3 times 2 is just 6. That's a little bit clearer. We get 4 root 6 minus 12. So finally, we get 4 root 6 minus 6. Hopefully I did that correctly. So yeah, you can also do FOIL with this. Okay, we're almost through the problems. So this is, again, not really a thinking question. Just more of a knowledge question. So if A is positive and B is positive, which is greatest? We have, so they look pretty similar, except that here the square is applied to everything, whereas here the square is applied individually on the inside of the radicals. So which one would be larger? I guess I'll let you guys think of this for a bit. Yeah, I'll give you guys like a few minutes to think about this. So which would be larger? So I'll just give you guys like maybe 1 to 2 minutes just to consider this. Um, so hopefully the hint kind of helped. Um, so you could try and evaluate these. So you could, maybe try to solve for root a plus root b squared, and then compare that with this simplified, which if you have the square root of like anything squared, that's just equal to the thing, right? So root a would just a squared would just be a, this would be b. So you're basically comparing a plus b versus this. So you could multiply it out. And if we actually did that, actually no. I think it's a little bit faster if you consider this hint. So if you have a plus b squared, so what we're just doing is we're just saying, let's say root a is equal to, let's say a, and that's confusing. I'll just say, let's say root a is equal to x, root b is equal to y. So what we have here then would be x plus y squared, which you might remember to be so not a squared, x squared plus 2xy plus y squared, right? So this is a really common form. You can also multiply it out, but it's, just faster if you know the form. And then here you would have, this is compared to this, which would just be uh and we're just going to actually multiply this out. So the square root of x is equal to the square, not the square, x squared is equal to root a squared, which is a. So a plus 2 root a root b plus y plus b is going to be what this is equal to. So you can quickly get that. And you're comparing this to a plus b. So you can see here there's this extra 2 root a root b term. And because we know that they tell us that a and b, they're positive, which means it's not going to be an imaginary number. If it's an imaginary number, there is no such thing as greater than or less than. But because they're positive, we know this is going to be larger. So it's the first one. So this is kind of just a callback to the a plus b squared form. So yeah. Okay, so we have some time left over. So I have just like this quick, just interesting, I guess like pattern here. And it's also related to what we just learned. So I'll just read this. So there's many tricks in mental arithmetic that involves algebra. So for instance, Cynthia claims to have an easy method for squaring any two-digit number whose last digit is 5. So for example, to calculate 75 squared, what you can do is you can, step 1, remove the last digit from the number you wish to square. So if I want to square 75, I'm going to get rid of the 5. That's the last digit. So now I'm left with 7. Step 2 is to add the resulting number from part 1 to its square. So it just means take the resulting number which is 7, and then add it to its square, which is 7 squared. So 7 plus 7 squared, which is a lot easier to do, which is 56. And then they just say, write the digits 25 at the end of the number you obtained in part 2. So 56, add 25 to the end of it. And this is equal to 75 squared. So that's pretty nice. We can try this for another example. Let's say I wanted to figure out what 24 squared was equal to. So what I would do is I would get rid of the 4, so I'd have 2. And then I would add 2 squared. That's equal to 6. So then this is, wait, this is not equal to 625 though. Oh, yeah, that's strange. Because I get 625. That doesn't actually work. Any two-digit number whose last digit is, oh, last digit is 5. Okay, I misread this. Oh, it's a very specific application. Okay, let's go with 25 then. So 25 squared, you get 2 plus 2 squared, which is 6. Add 25 to the end of it, you get 625. So yeah, 25 squared is equal to 625. Okay, I guess we'll try 65. So 6 plus 36 equals 42. 4, 42, 25 equals 65 squared. Let me just check if that's the case. So 65 squared. Yeah, that is 4225. Okay, so this definitely seems to work. But now they want us to show algebraically that Cynthia's method always works. And really, when they say always, there aren't that many numbers for it to work because it's very specific. It's a 2-digit number, that integer that ends in 5. So this is kind of interesting. We want to prove this algebraically. So something you could try to do is to express the number as 10x, right? If this was xy, you could say 10x plus y, right? You could think of that as a number. So like, for example, 75 would be 10 times 7 plus 5, which is 75. I guess you would start there. But then specifically, they say that y is equal to 5, right? It has to end in a 5. So it's really just 10x plus 5. Because we have a form 10x plus 5. And then we want to square it. And this is where what we learned today comes in handy. So now we just got to square this rational expression. So we're going to do that. So this is equal to 100x plus 100, or x squared, plus I think 100x plus 25, which is equal to 25 times 4x squared plus 4x plus 1. I'm not sure if this is going anywhere. I feel like this doesn't really go anywhere. Let's see here. So 2x, this is equal to 25 times 2x plus 1 squared. That doesn't really seem to explain Cynthia's steps, though. Yeah, they kind of just remove. Let's see if we can sort of do the steps algebraically. So remove the 5, so you're left with 10x. Although actually it's really just x because you're keeping the 7, right? So it's not 70, it's just 7. So you take 7 plus 7 squared. Then you multiply this by 100. And then you add 25. That seems to be what they're doing. Oh, okay. So I think I was supposed to factor it differently. So I should factor out the 100. Oh, and then plus 25. Okay, so you can factor this differently to get this result, which is basically what Cynthia's doing algebraically. Okay, I see. So they just want you to factor in a specific way. Yeah, that's pretty much it. All right. So next week we're going to be going over the inverse of a quadratic. So we're going to be going into a deeper dive into like the other types of functions. And then we might also go over exponential functions. And then a big thing in this course is going to be trigonometry and then also graphing trig functions, right? Like they're called sinusoidal functions. So, how do you graph sine x, cos x, and tan x? Actually, you don't have to graph tan x, not really, but sine x and cos x. So that's going to happen in like a couple of weeks. And then for homework, I'm going to just paste the link. So here's the link to the homework for this week. And ignore lesson 1 and lesson 2. So, because in lesson 1, lesson 2, they talk about exponent rules. We didn't really do that today. I'm saving that for another class. So just do lesson 3 and lesson 4, the worksheets, and then they also have solutions. And yeah, that's pretty much it for this week. I'll see you guys next week.